All right, that's taken care of already. That's good.
Perfect, my hero.
Okay, I'm gonna get some coffee while we wait for all these people to roll in.
Sounds good. I think we've only got 5, so I was going to wait a couple more minutes. I'm not waiting till a quarter after the
How about
devil's
8:30?
birthday. No. Dakota, how's it been? Has Walmart been insane?
Honestly, it's been getting better since the whole stay-at-home order. We
Good.
close down at 8:30, and we still have to stay for the normal scheduled time. So it's been dead like the last couple days. After 8:30, there's just nothing to do there.
Okay, so it hasn't been too outrageous. I
At
was
least,
worried about them like going to make you work 40 hours a week now or something really crazy.
thankfully, not. But it's at least it's not outrageous during like late evenings and all that.
Okay, good, 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 good. Oh, come on, guys. Good morning, Clarissa.
Morning.
I'm gonna have to get a new chair. My lawn chair is squeaky. All right, Cole's recording for us today, so we'll go ahead and get started. And if they miss anything, then they can just take a look back at that later. So basically where we were is working on section 4.1. Chapter 4 is all about doing some more solving. And with chapter 4, we're starting out with kind of an introduction thing as well, like we did in chapter 1. So let me see if I can't get to the share screen. It's not letting me. Come on. Goodness gracious. Hey, Brody.
How's it going?
Fine. Well, it was going fine until about 3 seconds ago when it's not letting me share this screen. Oh, there it is. Share. All right, got it. All right, everybody see the computer screen? Theorem 4.1, is it up?
Yeah.
Okay, great. All right, so the idea is the general solution is what we'll be looking for. The general solution is like the all-encompassing solution. Every single possible solution that could be found would be covered in this form. Maybe you find a solution that's got this piece, or maybe it just has this piece, but the general solution means no matter what solution you find, it's going to be some combination of this piece. So to make sure you have the general solution, in other words, there's not some function flying around out there that's also a solution that's not one of these guys, then you need to have a fundamental solution set. And what creates a fundamental solution set is a bunch of solutions that work when you plug them in, and they have to be linearly independent. If they are not independent, then they do not create a fundamental solution set. So if you have a bunch of solutions that work and they are independent of each other, then you can put them together to make the general solution. To check for independence, that's where you do that Wronskian, where you set up a determinant and you put your functions in the top row and you fill it up with derivatives until you make into a square. All right, and then we did this example. We went through and showed that both of these are solutions, or I may have skipped that part because it's pretty straightforward to do the second derivative and plug it in, and the y and plug it in and show that they equal to 0. And then the same for the other one. So we did that, and then we did the Wronskian, and was it -6? Is that what it was? Yeah, Wronskian is -6, which is not equal to 0, which means those two functions are independent. And so that means that the general solution, which is the all-encompassing, everybody's going to look like this solution. Nothing else will work unless it looks like this. Here it is, the general solution. And just a reminder that because it is a second degree differential equation, you need two separate linearly independent functions. All right, Dakota, we did lots of other stuff on Monday too, but that's basically where we were to pick up on.
Okay.
Okay, anybody got questions before we move on a little bit further? All right, here's the next one. Verify that for hyperbolic sine of 3x minus 5e to the negative 3x is a solution. So to verify it's a solution, we need a second derivative to plug in. So we need to do the first derivative. Who remembers what the derivative of hyperbolic sine is? Somebody make a guess at what the derivative of hyperbolic sine is.
2. Hyperbolic cosine.
Hyperbolic cosine it is.
Ha!
Hyperbolic cosine of 3x times a 3 for the chain rule. Derivative of the second piece, 5e to the negative 3x times a chain rule there as well. So that's going to be 12 cosh 3x plus 15 e to the negative 3x. Second derivative. Who wants to make a guess at what the hyperbolic cosine's derivative is?
Negative hyperbolic sine.
That's a good guess, and it's wrong. It's positive hyperbolic sine. That is so hard to remember and so easy to mess up because the others are not both positives and negatives. And then don't forget this extra chain rule here on this -3. So the second derivative is 36.
She set you up,
Since
bro.
I did, I set you up, I'm sorry. Minus 45 e to the -3x. All right, so to verify just means plug in and show me that it works. I don't want anybody missing another one of those on their next test, so I don't know how I can ask that question through WebAssign or Blackboard, but that's for me to figure out sometime later. Not today, I got too much else in my brain. Second derivative minus 9 times the original y is supposed to turn out to be 0. We got to make sure it in fact does turn out to be 0. And when you distribute, you get a -36 hyperbolic sine of 3x. Boom, those will cancel. And when you distribute this one, you get a positive 45 e to the -3x, those will cancel. So sure enough, equals 0. So it has been verified that it is a solution. Which shouldn't happen because we already verified that the solution to y second derivative minus 9 times 0 minus 9 times x, y equals 0. And this is the same equation. And we already verified that this is the general form, which means that no other form can take place. But I just showed that I could also get, where is he? This guy right here to work. So what gives? Thoughts, anyone? What gives?
Can you repeat that last part again?
I can. The previous example with the theorem, 7, the second derivative minus 9y equals 0. The general form of the solution is y equals c1 e to the 3x plus c2 e to the -3x. And general form means that is the solution. That is the only solution. It has to look like that. There's no other possible form that it could look like. It has to look like that. But this one doesn't quite look like that. So my question to you guys is, what gives? Thoughts, suggestions?
Doesn't hyperbolic sine have something to do with e?
Yes, sir. Very nice, Chris. Anybody remember what the hyperbolic sine's definition is? I didn't figure you did. E to the x minus e to the -x over 2. And hyperbolic cosine's definition is e to the x plus e to the -x over 2. And so if you look at these, you can also see why both of them are the derivatives of the other one. Remember a second ago, I snookered Brody into baited him in to get that negative. And there is no negative because the derivative of hyperbolic cosine is hyperbolic sine. Here's this negative for the chain rule comes into here. And that's about all there is to it. So that's why they are. So essentially, this is the format of this. It's just written another way. Moral of the story is, just because it's the general form doesn't mean if you can't sneak around and do something else with it. For example, if the general form has sine squareds in them and constants in them, you can always change that to cosine squareds using the Pythagorean identity. So make sure you're ready for that. So let's see, I'm saying that this is one solution, but I'm also saying it has to have this form, which is what the second part of the question is. Determine the C's. that are going to make that work. So 4 times the hyperbolic sine of 3x would be e to the 3x minus e to the negative 3x over 2 minus 5 e to the negative 3x. Sorry about my writing. My church pen's getting a little crazy on the stylus. And my x's look like alphas, but what's a girl to do? All right, so those will cancel to be a 2. And so we have a 2 e to the 3x minus 2 e to the negative 3x minus 5 e to the negative 3x. And if I put those like terms together, I can see that I, in fact, do have a solution of the correct form. Here's my C1. Here's my C2. So again, general form is the form. No other possible solution can be found except with the pieces of the general form, unless you can do some kind of tweaking like this one where it's the same thing, it's just a different way to write it. Questions on that one, anybody?
Hold up a second on that.
Okay, Holden.
So that minus 7e, shouldn't that have a negative 3x?
Oh, yeah. Yep. Thank you.
All right, so I see how we simplified that down. So we just say that the constants in front of both of those terms are those numbers in front of both of those terms are constants, or what?
Well, the general solution has C's in it, unless you had some initial conditions to solve. So in example 8, that solution, because when you have a differential equation, you start with the derivatives and you find the y equals. That y equals used to have C's in it, but they've already been solved for. Somebody already took care of that a long time ago. So the question is, what are the C's compared to the general solution? That's what the question was asking. What are the C's from the general solution for this solution? So the 4 sinh of 3x minus 5e to the negative 3x is a particular solution. What C's had to have been found for that one to work? Kind of backwards. And what we'll be doing the rest of the chapter is not verifying. We'll be solving and finding the solutions ourselves. And if you can factor, you'll be good. If you can't factor, it's going to be a roller coaster. All right, example 9, given 3 functions that satisfy the third order differential equation. In other words, they work when you plug them in. We could verify this, but we're going to skip that part because it's going to take a while. I can do this one really quick. The first derivative is e to the x, the second derivative is e to x, the third derivative is e to the x. So plugging in, I would have an e to the x minus 6 e to the x plus 11 e to the x minus 6 e to the x. That's going to be 12 minus 12 e to the x, which is 0. We could verify all the others as well. You're going to get some coefficients because of the chain rule timesing by 2 a bunch of times, but they'll all turn out to be 0. So verify, don't forget how to verify. So we're going to assume that's correct. Those are all solutions to the differential equation. Third order differential equation because there's 3 derivatives. This differential equation is linear because it is a function of x times the derivative of y, function of x, derivative of y, function of x, derivative of y, function of x, plane y, function of x. So it also happens to be linear. We are going to find the general solution, which means an all-encompassing, every solution has to take this form. We'll define the general solution of a third order differential equation. You need 3 independent solutions. I have 3 solutions. I need to make sure they're independent. To make sure they're independent, you have to determine that there are no possible C's except 0, 0, 0, for which you can put these 3 together and be 0. But you would have to exhaust every possibility in the history of the world of C's. And so we don't usually do that to check for independence. It's easy to make some C's, make it 0 to show that they are dependent sometimes. Sometimes it's not easy, but sometimes it's easy. If you want to show that they're independent, instead of messing around with infinitely many C's, you want to check the Wronskian. And to do the Wronskian, you fill up the first row with the 3 functions that you're checking for linearly independent. You do derivatives. You fill up down each column until you make a square. So down the first column, derivative of e to the x is e to the x. Derivative of e to the x is e to the x. Next column, you just got a chain rule going on. Derivative of e to the 2x is 2e to the 2x, and the derivative of 2e to the 2x is 4e to the 2x. Next one, chain rules again. And if the Wronskian is non-zero for any possible x, because it has to be non-zero, if that is the case, then you have a fundamental solution set which allows you to write the general equation using these 3 fellas. But it has to be linearly independent or it doesn't count. And we wouldn't know where to go on this equation because we haven't practiced solving them yet. So to do the Wronskian, you just do a determinant. I am a column 1 girl. I know that most of you guys use the top row to do your determinant. Like it's the same as cross product if you're thinking about vectors, but I always use column 1. So I'm going to go ahead and take off with my column 1. For those of you who haven't done any in a while, set aside whichever piece you're using. Mark out the row and the column that it's in, and then do the determinant of what's left. Multiply these 2 first, 18 e to the 5x, minus, always a minus, 12. I mean, it could be a plus if it's minus a negative, but it's always a minus. Minus 12 e to the 5x. What happened to my eraser? And, oh, I said do not revert to pen after use. Oh, now it's a no. Okay, pretend like I'm going to erase those. All right, I'm going to move on to the next one. I use column 1 or row 1, so I'm going down that way. My next one is e to the x. Remember the sign pattern goes like this. So if you use the top row, you'll be changing the middle one. I use the first column, so I'll be changing the sign of the middle one. mark out the row and column it's in, and then do the determinant of what's left. The down is 9e to the 5x minus 4e to the 5x. And then my last piece is e to the x, row column, 3e to the 5x minus this one, 2e to the 5x. And then simplify all that mess. This is going to be a 6e to the 5x and another e to the x. So that'll be a 6e to the 6x. The next one will be a 5e to the 5x times negative e to the 5x will be negative, or I'm sorry, negative e to the x will be negative 5e to the 6x. This one is 1e to the 5x. Make it e to the 6x. And so if you add those like terms, you get 1 plus 1, which is 2e to the 6x. 2 is a positive number. E to any power is a positive number. Any exponential graph looks like, no matter what the base, looks like this. It's always above the axis. It's always positive. That is greater than 0. Since the Wronskian is not 0, the Wronskian doesn't have to be greater than 0. It just has to be non-zero. So definitely if it's positive, it's not 0. Because of that, then your general solution can be made up of your 3 linearly independent solutions with some constants slapped on the front. And if you had some kind of initial condition or boundary conditions to work with, you could be solving for those C's. All right, floor's open for questions on that one. Somebody say something so I know you're all still there.
I don't like it.
Okay. You don't like it because the Wronskian?
Yes.
Yeah, well, that was a pretty easy Wronskian. So wait till they get some signs and quotient rules and product rules and some nastiness in there. You're really not going to like it. But never fear, you shall survive. This is your last math class. Remember, gentlemen, last math class.
I can't wait to use this every day.
And I just heard, do what? I don't think you're going to use it every day. I don't know what you're going to use it for, but
That's what I'm
telling you,
saying.
Russell
We're not going to
Wolfring-
need to know this.
You don't think so? You're guessing. I think you need to know some of it, but I don't know what for what. But that's a whole nother conversation that we could get off on for years. All right, next thing is if you don't have a homogeneous, you have a non, I swear I had yellow as an option. You have a non-homogeneous equation, which means it doesn't end in 0, it ends in a g of x. So basically what you do for non-homogeneous is you pretend it does equal 0, and you ignore the g of x, and you work it out exactly like you would if there was no g of x. And then you tack on one extra step at the end. And that extra step at the end is to add on a particular solution. And for now, we're just verifying again, but for later, I'll show you how the steps will work when we start these fellas from scratch. All right, here is a particular solution. A particular solution no C's in the particular solution. This one we already did. We already solved for the general solution of this differential equation. The homogeneous solution, this is the same one from the last page. So the solution to this one, the general one we already found, was y equals c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. That's already been done. So this is just that final extra, do one more part because it's not homogeneous. So if I was solving y triple prime minus 6y prime plus 11y prime minus 6y equals 0, I would be done. The general solution is done. But with it being a 3x, you ignore the 3x, you solve it like you normally would, and then you go back and do an extra piece. Well, the extra piece would be solving for this one. And then for the final answer for your y, you just tack that on to what you already have. I'm thinking that's a negative. I don't know, you think that's a positive 11 or negative? I think it's a negative. We're going to verify it in a minute, so we'll find out if it's not. So the full general solution, just tack it on and you'll be done. Okay, but the first thing we need to do is actually do the verify or prove or show. So to show, verify, or prove, you just have to plug this fella in to the differential equation to show that it works. To do that, we need a first derivative and a second derivative and a third derivative. The first derivative is -1/2, and the second derivative and the third derivative are both zeros. So plugging it in, I get a 0 minus 6 times 0 plus 11 times the first derivative minus 6 times the y that I started with, -11/12 minus 1/2 x. So that's going to be -5.5 plus 5.5 when I distribute, and then plus a 6 or plus a 3y when I distribute that 6. I'm wanting y's today. That's a 3x, which is exactly what I'm supposed to get. So it is verified. It is a solution. It is called a particular solution because it doesn't have any c's. So for the one that we just did, we just have to tack that on. Now finding the solution for the triple prime minus 6 double prime plus 11 y prime minus 6y is actually not a whole bunch of calculus at all. It's mostly algebra. So while it seems like I'm just getting those 3 equations, those 3 e to the x's out of nowhere, they're really easy to find when the coefficient functions are integers. And we'll talk about that later in this chapter. All right, and then the last is just tacking on one more layer. So if it's a differential equation that equals 0, you'll find your general solution. If it's a differential equation that doesn't equal to 0, you'll find your general solution, then you'll find a particular solution, and then you just tack them together. This last theorem is one more layer to it. If you had this one equal to 0, you'd find your general solution. And then you find a particular solution for all of this stuff. But the last theorem allows us to not do it all together. The last theorem allows you to piece it into parts. So if you have this as a particular solution for this piece, great. And you already know that this is a particular solution of this piece only. And if you know that this last one is a particular solution for this piece only, then you can just tack them together. And so your general solution would be the general solution that you get for the second derivative plus 3y prime plus 4y. Then the particular solution, you could just tack them all on. So there is no general solution for this one because there were no, let's see, it's a second order differential equation. We would have to have two equations that worked. We would have to show that they are independent. Then we'd have to do C1 times the first one plus C2 times the second one. That will give us the general solution. Then we could have to go through and show that all of these worked when you plug them in. This works when you plug it in. This works when you plug it in. Then you can put it together to make a final particular solution of all three of those guys plugged in at the same time. And we're not going to get to any like that we're doing from scratch that have all that many pieces, but we do have some that we will check out. All right, messy, messy, messy. Questions before we close out section 1?
Can you go back? Can you go back? I had to finish that equation.
Probably too
I
late.
thought you'd give me like 3 seconds.
I
Not 3
did. There
seconds,
was
it's
a
there.
wait time. Tell me.
I have
what
2e to the 2x plus something.
Oh, 2e to the 2x plus 2x e to
Okay.
the x minus e to the x.
2x e to the x? Okay. Minus e to the x. Okay. That works for me. All right. Thank you.
You know what? That wasn't even right. I showed you the wrong one anyway. That was just not good. Hold on.
Well, I appreciate that.
I just wrote down the question and not the solution. The solution is putting together all the solutions. I just rewrote the question. This is the particular solution. You put the first part, particular solution together, second part, particular solution, third part, particular solution. That'll make a lot more sense though when we get to where we're doing them from scratch. I don't dislike how this author sets up the textbook like an introductory thing and then comes back and puts pieces together. But I know that, I don't know, that's the new discovery approach stuff. Show you why you're going to do it first and then do it. But I think it's confusing if you don't start at the beginning and build up the pieces. But anyway, who am I to say? I'm just an instructor, not a guru. All right, section 2. Section 2 is actually, okay, back to there. Is everybody here today? Let's see how many we got. 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 13. Who? All right, moving on. Section 2 is reduction of order. And section 2, you use this process if you have one solution already. If you don't have one solution already, then reduction of order is not going to work. So why would you have one solution already? Well, sometimes it's just given and there's no way you would have come up with it on your own. But other times there's an obvious one solution that would work. You could just look and say, oh, hey, I think this would work. Oh, yeah, it does. And then you can use it to find a second solution. So reduction of order is what it's called. It's called reduction of order because we're going to take a second order differential equation and turn it into a first order differential equation, which means instead of having a second derivative, you're going to have a first derivative. And if you only have a first derivative, you can separate or use an integrating factor. So that's how we're going to finish, with an integrating factor or separation to be integrated. Reduction is used for a homogeneous differential equation, which means you got to have an equals to 0. So not going to work for something else. This video here is one of Patrick's. It shows why reduction of order works. You can look at it if you want. I will post it. I don't have videos posted yet for this section, but I will get them posted hopefully by the end of the day today, definitely by the end of the day tomorrow. So there's a little video on why reduction of order works. So take a look at that if you're interested. If you don't want to know why, you just want to know how to do it, then don't take a look. All right, so 2 examples for this one. I hope we get, and I'd like to get through both of them today. We shall see. So here is a second order differential equation. It's second order because it has a second derivative. It's homogeneous because it's equal to 0. I do not think it's too much of a stretch for me to ask you to look at that and tell me a solution. The second derivative minus the original function gives you 0. What function has a second derivative that is the same as the function you started with? Of course, e to the x is a function that has the derivative the same as what you started with. So the second derivative of e to the x would be e to the x minus e to the x would be 0. I don't think it's so far-fetched to expect you to be able to look at that and determine that solution. I might have to pry it out of some of you, but I think that's something you can do. Can you look at this one and say, oh, shoot, I know a solution. X squared is a solution. Probably not. Okay, but on example 1, I do think it's a fair question. So the process, when you have one solution given already, to find a second solution. Why would you want a second solution? Because this is a second degree differential equation. If you have 2 solutions that are linearly independent, then you can put them together and get this general solution, which is the all-encompassing, everybody's got to look like this, there's nothing extra out there floating around solution. Questions thus far? Speak now. Somebody at least say this is going to suck, so I know you're all there. Oh, but you're cutting out a little bit. Can you guys hear me still?
Yeah.
Yep.
Okay. Okay.
Oh, we're just doing great over here.
Oh, fantastic. You've had your coffee then. All right. So how are we going to do it? We are going to use this substitution right here. Y equals U. Hey, U substitution. We like U's. And Y1. Y1 is the one that we already know. So we're going to use the solution that we already know to substitute in U times Y1. We're going to make that Y equals. We're going to do some derivatives, plug in, and then it's going to turn into something that is either separable or an integrating factor. All right. If you're ready. All right, I was wondering about that. I didn't have any pages, so I was wondering if I went to a second page, if it would give me some lines to write on. That's kind of nice. All right, so number one, my y1 equals e to the x. And my equation is the double prime minus y equals 0. My u substitution is y equals u times the equation I already know. E to the x. I know e to the x works. I am going to do a substitution. That means I've got to sub all of this stuff into my equation. And to sub all of that stuff into my equation, I have to have a second derivative because the second derivative is what comes first for my substitution. So I'm going to have to do the derivative of this fella not only once, but twice. So the first derivative, and u is not a number, u is a function of x. And so you have to use a product rule. First times the derivative of the second plus the second times the derivative of the first. I'm going to use a prime notation. And then the second derivative is two product rules. The first times the derivative of the second plus the second times the derivative of the first. Product rule for the next one. The first, the derivative of the second this time is a second derivative plus the second times the derivative of the first. And putting some like terms together, those, I don't know, these two fellas here are alike. So we just have a u e to the x plus 2 e to the x u prime plus e to the x u double prime. Everybody with me so far?
Yep.
Great. Anybody need a 10-second timeout?
Nah.
All right, then here we go. We're going to plug that into the original equation. And so we're going to have that y double prime, which is going to be a struggle to fit, but I shall make it work. Minus plain old y. And plain old y's name is right here for substitution, e to the, or u e to the x. And it's homogeneous, so it's equal to 0. And a beautiful thing happens. Any term that has a u in it will cancel. Any term that has a u in it has to cancel, or you can't finish. So if your single u's don't cancel, not the primes or the double primes, the single u's do not cancel, you have made a mistake. So make sure you're careful on that. And so what do you have left? 2e to the x. I'm going to go ahead and factor that e to the x out because I'm going to need to do it in a minute. So I'm going to go ahead and do it now. Make my life easier. I have a product of two fellas, e to the x times something else. And that product is equal to 0. The only way to get an answer of 0 when you're multiplying two things is if somebody's 0. I don't know why that gets to be called a rule, the 0 product rule, because it's kind of a duh. Can't have a positive times a positive or a negative times a negative or a negative times a positive. You have to have somebody be 0 or you're not going to get 0. And e to the x is an exponential that looks like this, and e to the x never hits 0. So it cannot be that one that's equal to 0. It must be this one that is equal to 0. Anybody got any beef so far, or are we okay?
Couldn't you plug in negative infinity for x?
To
Or
get 0?
yeah,
So like negative 3,491,281.
close enough.
That's still not 0. It's like 0.0000000. Close enough is sometimes in science, but not in math. Not close enough, because we don't want it to be close to 0. We want it to be equal to 0. So yes, you can plug in and get it close, but you're not going to be able to get it equal. I told you the story about the scientist and the math and the cat house, right?
No.
Okay, I'll tell you later because we got to get on this. All right, so here's what happens, and this is why it's called a reduction. When all of those things cancel, nice things happen, and you can't integrate this as of yet. We'll be able to integrate some second degrees soon, but you're going to make a substitution, and your substitution after u is always w. So we're going to make w equal the first derivative, and then if that's the case, then the derivative of w would be the derivative of the first derivative, which would be the second derivative. You're always going to have two substitutions in reduction. The first one is going to be y equals u times the function you already know. The second substitution is always going to be this w business. And so what happens is it turns that equation into this one, 2w equals, or I'm sorry, plus w prime equals 0. Well, everybody in this rascal is functions of x. Y is a function of x, u is a function of x, everybody's functions of x. So another way to write this is dw dx. And lo and behold, this turns into a separable differential equation. You could use an integrating factor if you want. I don't want to use an integrating factor. I just want to separate it. Divide that negative 2w over, multiply that dx over, and now you're ready to integrate. You got a whole bunch of derivatives and integration floating around here, so make sure you're careful with all your rules. Like your first substitution, the y equals u e to the x, you've got to do a second derivative just to be able to plug it in. So you got product rules and all that stuff going on in there. And then when you plug it in, it turns into separable or an integrating factor, which means you're going to have to integrate. So your derivatiing, I don't even think that's a word, but you're separating, integrating, all this at one time. You got to make sure you pay attention, especially with like sines and cosines and those negatives that get you sometimes. So watch out. Everybody good so far?
Yep.
Do you want to keep the 2 there, or do you want to leave the 2 over with the dx? Now that I have it right there, I'm thinking I would rather just have left it over here. Make it easier to integrate. I don't want that. Oh, I think I'll leave it right here. All right, new page. Oh, come on. You won't let me add a page. There we go. I got this app, and every time I want to do something, it not every time, but a lot of times I want to do something, it says, yeah, you can do this if you upgrade for $2. I'm like, dang it. So I needed to be able to have more than one file, so I had to pay $1.99 to upgrade for more than one file. But I'm afraid they're gonna like get me like 10 cents here, 20 cents there, drive me nuts. All right, so left side, natural log absolute value of W equals right side negative 2x plus C. Now, those are nice, easy integrations. So I hope you had already knocked that out. Please tell me you had. I'll assume you're all shaking your head yes. We need to get this fellow back to where it started, and it sure tootin' did not have a W to start. So we're going to have to get that W out of there and get back to where we came from. But unfortunately, to get to the W, we came through the U. So we have to get the W back to a U and get the U back to Y's and X's. So that's going to be not difficult, but kind of a windy road. Because it's easy to solve for W, I'm going to remember this is automatically base E because it's a natural log. E goes across, bumps up the negative 2x plus C, log rolls off. Absolute value of W, but once you bump with an E, it's going to be positive automatically. E to the negative 2x plus C. And don't forget about that being E to the negative 2x, E to the C, which is why that C comes down front as a constant, times on, not added. I know it's been a while since we've talked about that. I know we talked about it a lot, but don't let that mess you up now that it's coming around again. All right, so what was W? If you go back to the last page, W was U prime. And U prime, since U is a function of X, is du dx equals C e to the negative 2x, which is also a separable differential equation. And then you can integrate. The integral of du is just going to be u. And the integral of this one on the right is going to require a plus c. You've already got a c there. So you better mark one or the other some way, shape, or form. Asterisks, stars, C1 and C2 is a logical choice, but whatever you want. We got a chain rule to compensate for here. Really, we're doing u substitution, not to be confused with the u we already have. Negative 2x du equals negative 2 dx. So negative 1/2 du equals dx, which is where the negative 1/2 is going to come in. Negative 1/2. And then the C1 e to the negative 2x plus C2. Although a constant times a constant is just a different constant. So if you do forget the 1/2 on this one, you're going to be fine because it can absorb into that negative 1 or to that C1 anyway. Now, if you had started plugging in and solving for C1s and C2s, you can't go changing your C's to different C's. And we're still not quite done because we didn't start with U's. We started with Y's. And the original substitution that we did was Y equals U times Y that we already knew, which means Y equals U e to the X. And so another name for U is Y over e to the x. And finally, we can get back to y equals by multiplying both sides by e to the x. C1, e to the negative x. Do not forget this fella also gets the e to the x. There is a second solution. Oh, doggone. Get back there. There's a second solution. In fact, there's lots of options for a second solution. Any linear combination of C1 and C2 is a second solution. You could have your second solution be 1 e to the negative x, 2 e to the negative x. You could have your second solution be pi e to the negative x. You could have your second solution be, I guess technically 3 e to the x, although that's really a linear combination of one of the solutions you already knew, so that's really not fair to do that one. You could have your second solution be 35 e to the negative x plus 510 e to the positive x. Multiple options for your second solution. I think the most obvious option is this fella right here. We already have the e to the x one given, so the logical second solution would be e to the negative x with the easiest leading coefficient of 1, since I get to pick it. All right, so the process. Substitute. Do the derivative so you can plug in. Any term that does not have, or any term that has a single u in it has to cancel. Then you have to substitute with the w so you can separate or integrate with integrating factor. Then you have to do that integration. Then you have to get back to u's. Then you have to do a second integration. Then you have to get back to y's. Whew, then you're done. Questions? Nick.
Hello?
Oh, just checking if you had a question.
Yeah, I don't really understand how you said like we can plug in like the pi e to the negative x or the whatever. I understand like how we got just regular e to the x.
Okay, so the question was just to find another solution. This business here is another solution, and you can pick any solution you want with any constants you want. I'm just saying you can throw in a C1, a C2, however ugly or pretty you want. You can do one or the other, or you can do both to get your second solution.
Okay.
That's all. Usually the obvious solution is the one that doesn't have the piece like what you started with. And the piece what you started with is always going to come out in part of it somewhere. So usually we just pick the opposite one and use a C1 equals 1. But you don't have to. You can use any ones you want. Anybody else? All right, here's my claim. My claim is not only that this is another solution, my claim is that this is the general solution. The general solution means every single possible solution is going to be of that format. Now, I know that since I have a second derivative in my equation, and that's the highest one, so it's a second order differential equation, that I have to have two solutions that are linearly independent to create the general solution. Well, I do have two solutions, e to the x and e to the negative x. That one satisfies the differential equation. And this one would be a second derivative minus second derivative is a positive. I got my negatives messed up in here. First derivative will be a negative, second derivative will be a positive. They both satisfy the equation, so I have two solutions. The other thing that I need for a general solution is I need them to be independent of each other. To check independence of these two solutions, I can do a Wronskian. Derivative, derivative. Wronskian is this way, negative e x plus negative x is 0, minus e to the negative x plus x is 0. That's going to be a negative 2 for the Wronskian, so it is not equal to 0, which means these are independent solutions. Brody, you like that Wronskian better than the last one? Brody, did you leave me? Dang. Anybody else like that Wronskian better than the last one? So I know you're all still there.
Much better.
Yeah, can you do a flyer homework? I gotta learn two
Oh,
songs.
math part.
All right. So I have two independent solutions that both work. That means this is the general solution, which means every single other solution to this differential equation has to have that form. I guess it could also be like the hyperbolic sign of something because that would have that form, but because it's got all those e to the x's running around in it. All right, reduction, that's how it works. Questions on that one before we start number 2? All right, number 2. Okay, $5 for page 6. Oh, no, all right, great. All right, number 2, this solution that we have already is y equals x squared. The differential equation is x squared y double prime minus 3x y prime plus 4y equals 0. Since x squared is a solution, you should probably double check, especially if it's a test time writing, that x squared actually is a solution. The first derivative would be 2x, the second derivative would be 2. That'd be 2x squared minus 6x squared plus 4x squared. Yep, it is 0. Good news, no typos. All right, substitution is always y equals u times the solution that you already have. First step is always to do the derivatives how many ever you need to plug in to this equation. So we're going to need a second derivative, which requires a first derivative first. First times the derivative of the second plus second times the derivative of the first. Then the second derivative. First times the derivative of the second plus the second times the derivative of the first. First derivative of the second plus the second times the derivative of the first. Are there any like terms there? It looks like these two guys can go together. And then we can plug in. It's going to take several lines, I'm thinking. So plugging in, I have x squared times the second derivative, which is 2u plus 4x u prime plus x squared u double prime. X squared times the second derivative. Minus 3 times x times the first derivative. Um, 2ux plus x squared u prime. Plus, last one is 4 times y, 4u x squared. 4 times y equals 0. Distribute like terms, get your use to cancel. A 2ux squared plus 4x cubed u prime plus x to the 4th u double prime. Don't mess anything up. What's next? Minus 6u x squared minus 3x cubed y prime plus 4u x squared. U's better be canceling. All single U's. Two and 4 is 6 minus 6. All right, everybody good to go to the next page?
Yeah.
Okay. If you get to that spot and the plain U's do not cancel, you have done something wrong, so make sure they do. I wouldn't just get rid of them in case there's something else that you've done wrong. All right, so that puts us with what is left, and there's two like terms there with what is left, so double check yours. should have next to the fourth u double prime plus x cubed u prime equals 0. Once you get that done, your next step is always going to be to do the w thing. W is always going to be the first derivative. W prime will be the second derivative. So we'll have x to the fourth. The double prime u will be a single double u prime. Ooh, that's crazy mouthful. X cubed w equals 0. On the pre-written notes, I think I said this was not separable, but it is separable, so I don't know what I was thinking. X to the fourth dw dx plus x to the third w equals 0. I think most of you prefer separation, so not that an integrating factor is hard on this one. An integrating factor is pretty easy also, but I usually separate when I can. I don't know what I was thinking saying that one wasn't separable. If you printed the pre-printed, I did an integrating factor on that one. All right, so to finish up, which we will save for next time, we're going to have to integrate once to get the w solved. Then we're going to have to plug back in for the u. We're going to have to integrate again to get the u solved. Then we'll have to plug back in for the y. But we're set up to, go downhill pretty fast here to finish. Should not take too terribly long. And I know I said I was going to go to 9:30, but I didn't know Hofflick was doing the Zoom. So let me get out of here if I can. Well, I'm trying. It's not wanting me to get out for sure. All right. All right. Who has questions for me before you go? First of all, who's all here so I can mark down, see who I need to talk to about making sure they're good. Nick, Eduardo, Chris. One, two, three, four, five. Cole, too. I'm so confused.
He went to the bathroom.
Why
And
is he in
then-
here?
I've been here the whole time. Hold up.
You had to leave and come back
Goodness.
or what?
No, long story. I don't want to explain it.
Okay, don't explain. Somebody tell me who's not here. I don't see Nathan today. No Blake. Nick, you're gonna have to get on to Blake.
Chase Reed.
Do what?
Chase Reed.